Hi everyone, my name is Miles Zoner. For my presentation, I chose to present on the paper titled AURORA, Statistical Crash Analysis for Automated Root Cause Explanation. This paper introduces a framework to help identify the root cause for crash-causing inputs in a target binary for a fuzzing campaign. This paper was introduced at the USENIX Security Conference in 2020. A little background on the authors for this paper. This paper came out of the Rural Universität Bochum from Germany, and its authors include Tim Blazitko, Moritz Schlogel, Cornelius Aschermann, Ali Abbasi, Joel Frank, Simon Warner, and Thorsten Holtz. These are many of the same people, and also it's the same university, where many papers such as JIT picking, differential fusing of JavaScript engines comes from, as well as Loki, which looks at hardening code obfuscation techniques against automated attacks to try and prevent deobfuscation, as well as Red Queen, fuzzing with input to state correspondence. And these all have many people in common between all the papers. First, a little background on fuzzing. What is fuzzing? So fuzzing, which is an abbreviation for fuzz testing, attempts to explore a program's input space for bugs and vulnerabilities. It is a very automated process that, once set up, requires very little input from the human user. It explores the input space of a program to try and effectively look for bugs and vulnerabilities through crashes. While other different security oracles can be used to try and determine if a security violation has occurred for a given input. Crashes are the most common, and I will go into that a little bit later. But first, for my explanation, I will be using AFL++ as my example to help explain fuzzing. There are other fuzzers available, but AFL++ is one of the biggest and most commonly used. AFL++ explores the input space of a program to look for vulnerabilities by mutating certain seeds, like initial seeds, in order to try and change those in order to explore more of the program and more execute the different parts of the program that are being executed. So initially, there's a set of seeds that you will give AFL++ to input into the binary, and I'll try and change those to try and find more stuff. Typically, you want those seeds to explore as much of the binary already by themselves, so that AFL++ has more to work with. AFL++ is also a gray box fuzzer. This is contrasted with white and black box fuzzing. Black box fuzzing, if you're familiar with black box in general, means that no internal state of the program is visible to the fuzzer. That means that for any given input, the fuzzer is blind to what is happening inside the program. This is used if very little can be known about the program. However, it's not very desired due to the fact that it gets no feedback. So therefore, whatever inputs it gives to the program are completely blind, and it only knows if it crashes or not. This is also contrasted by white box fuzzing, which often involves extensive program analysis in order to efficiently try and explore the input state of a program. AFL++ is none of these. It's gray box because it gets its information about the program through compile time instrumentation. What this means basically is that the program, in AFL++'s case, is compiled using a custom compiler that inserts code, right, or instrumentation into the binary that says whether or not certain edges or parts of the program, the system under testing, the target binary, are being executed. Once these, so when AFL++ runs a given test case against the binary, AFL++ is able to tell what parts of the program are executed and how many times they're being executed in the case of loops, which can often be more or less loops depending on the input, and records that and is able to tell if a mutated test case explores more of the program, which is good, right? And so that's why it's gray box. And so, yes, given the information that is output by the system under testing, If it explores more coverage, then if a plus determines it interesting and adds it to its corpus of seeds or inputs. So why do we care about crashes? Well, as we said before, they're an easy way to detect possible security violations. If a program crashes, that's very easy to detect on modern computers. However, can anyone guess why all these crashes might cause a bottleneck in the fuzzing campaign? That's because it's very difficult to determine what's causing these crashes by automatically. It often requires a human to intervene and determine what's causing these crashes. And because there's so many of them that can be created by a fuzzing campaign, it's very necessary that this process of determining what is causing these crashes is automated. That brings us to our next topic. Triaging. Triaging is determining why a given crashing input causes a crash. During this process, many different crashes are analyzed and grouped depending on what is causing them. Another difficult part of triage is that just because of that the root cause is not this, where that's located inside the binary, is not the same as the location of the crashing instruction. Because of this, manual effort also dominates a lot of the time that it takes to try and fix these bugs. First, the triaging method I'm going to talk about is often the most common and traditional one, debugging. Debugging involves manually inspecting the program to see instruction by instruction what's causing the crash. Typically, how this works is using a debugging framework or tool, such as the ones I've listed here, such as GDB, Radari2, IDA, or Binary Ninja. Of course, there are many more, but these are some of the ones that might come to mind when you think of this process. What you do first is start this crash instruction. This is very easy to find out because it's what typically happens last whenever a program is when a program crashes. From there, different values and aspects of the program are inspected, such as registers, the stack, heap, control flow of the program, as well as other values in memory and from the CPU. You mainly reason backwards from the crashing input to try and figure out what causes the crash, the root cause of the crash. And this process also gets much more complicated and error-prone the larger a program gets, as well as slow down. Because of this, debugging is a very slow process and requires a lot of effort. That brings us to our next triaging technique, sanitizers. Sanitizers are another way of trying to figure out what's causing a crash. How these work is that at compile time, similar to instrumentation for fuzzing, it adds checks to the programs to try and figure out what errors are happening and also what's causing them. I have two different sanitizers listed here, but there are other ones. The ones I have here are the address sanitizer and the memory sanitizer. There's also, for example, the undefined behavior sanitizer, which can help identify cases where undefined behavior is being used by a program, which is not good if different compilers are compiling a program. There's also different ones, for example, for kernel stuff, but these are the ones we're concerned about for now. The address sanitizer deals with memory corruption. So that's things like use after freeze, buffer overflows, that type of thing, which makes up a majority of bugs and vulnerabilities. And the memory sanitizer, which deals with uninitialized memory, which can also cause crashes to be found during fuzzing campaigns. Here's an example of how a sanitizer can work. In this case, the address sanitizer. What we see on the top here is how the malloc typically behaves, where it tries to pack in memory allocations on the heap as closely as possible. What can happen though with buffer overflows is that values can be read or written to into nearby cells if there are not proper memory checks. How the address sanitizer tries to detect this is that instead of tightly packing memory allocations as tightly as possible, it puts space in between them and marks memory as either valid or poisoned. This way, if a memory access, such as a read or write, is used, the address sanitizer can determine if that read or write was valid or poisonous. And if it's poisonous, that's indicative of an attempted buffer overflow, which is useful. However, there's some drawbacks to techniques I mentioned, such as they can't find everything, and also they don't always work for every single type of memory vulnerability. So, and there's also different types of triaging techniques that are not mentioned, such as backward taint analysis and reverse execution, which trying to work backwards from the crashing to find what's causing the crash, the root cause. However, these also can fail, such as when there's no direct data dependency. And so this is where AURORA comes in. So AURORA tries to automatically identify the root cause or try and help find the root cause for a crashing input. It tries to guide the crash triaging by outputting known predicates, which are binary statements about a program to help identify what's causing it to crash. And also, it works better than some other things, such as the sanitizers, in that they also work with binary-only programs. And AURORA does not require the source code program to work with it. And it's also able to handle bugs, such as ones with no data dependency, that other typical triaging techniques cannot work with. So the idea behind AURORA is that the crashing behavior for input or the crashing behavior for a program is not the same as the regular behavior for a program. So they must differ in a meaningful way. And another idea that motivates AURORA is that the earlier in a program the difference is between execution for crashing and non-crashing input, the more likely it is to be related to the root cause. And so I have a graph here that shows that typically a program will have more differences near the root cause and the crashing location. And of course, we're mostly interested in the root cause because we already know where the crashing location is. So in order to find these two different, in order to analyze the behavior between these two different inputs, the crashing inputs and non-crashing inputs, we have to have a set of non-crashing and crashing inputs to work with. AURORA tries to look for behavioral differences in these two and tries to rank differences in the way that best predict crashes. But of course, when you talk about the different inputs, the crashing inputs all try and have the same root cause because they all should try and behave in a similar way, but also provide enough set to show to help guide statistical analysis. And the non-crashing inputs are unrelated to each other. They don't have to be related to each other because they only form a baseline for how the program is supposed to behave compared to crashing inputs. Of course, however, we need a large enough set of input to work with. And to do that, we use crash exploration. Crash exploration allows us to try and find many related crashing inputs because it's difficult to find that by yourself. So crash exploration is actually a built-in feature of many fuzzing frameworks, such as AFL++. And how it works is, given an original crashing input, you put it gets put to the mutation engine and fed into the SUT, or the system under testing. If the SUT crashes, we then keep that new crashing input, right? And hopefully, because we're mutating the original crashing input and getting this new input, the underlying issue that's causing both these inputs to crash should be related. And if the SUT doesn't crash, we don't really care about in this case and we discard it. However, this is only useful for finding crashes and it doesn't really help us in our case where we want non-crashing inputs. And in that case, the team behind AURORA patched AFL++'s crash exploration to also find non-crashing inputs to get a large set for statistical analysis. AURORA uses these things called predicates in order to describe the behaviors that help to identify crashing and non-crashing inputs. These are Boolean statements that take the form of true or false to identify if something helps identify a crash or not. They are local to each instruction, and every instruction can have multiple different predicates. These predicates identify certain things, such as different parts of the program that are taken, different values like maximum and minimum values in registers, and different flags that are set by the instruction. So these can be true and false. For example, we have an example next slide actually. In this case, it says that for the given instruction at address, I won't read it out loud because it's too long, that the RAX register is less than OX11 or 17 in decimal. It also gives it a score, which we'll talk about later in the presentation, as well as the disassembly of at that address, what the processor is actually doing. It also shows the address to line, or the address that the instruction relates to, if the given source code was given to Aurora. And so we can see here, it says that that register has the value less than 17. And so it could also be something else, such as if jump if less than or equal to thing was taken for that same line, or not in this case, but you get the idea about how it works. And also, how do we get these predicates? Well, Aurora uses a program or a tool from Intel called PIN, which is able to trace the program and create predicates regarding the program's behavior for any given test case. And so for PIN, they made a PIN tool that is able to identify what different behavior is being taken by input and record that for the predicates. And why PIN is useful in this case is because it doesn't require the source code to trace the program, enabling it to work in closed source binaries. PIN works by taking in the program's binary into its own memory, and also using its just-in-time compiler in order to add instrumentation and execute that to be able to identify what is being done to the program. Earlier, we talked about how Aurora scores predicates. Well, this is based off of two different metrics. First, Aurora scores predicates based on how well or accurately they describe if the input is crashing or not crashing. If if a predicate is always true for every single crashing input at a certain address and always false for every non-crashing input at that address, we can call that a perfect predicate. For example, the example we gave earlier, where for a given instruction, RAX was less than 17. If that was true for every single crashing input and false for every single non-crashing input, that would be a perfect predicate. We can compare this with imperfect predicates, which is not wholly able to differentiate between crashing and non-crashing inputs. So for example, if a predicate for a given instruction was always true for every crashing input and also true for a subset of the non-crashing inputs, but false for the rest of them, that would be an imperfect predicate. And while it's not a perfect predicate, it can still be useful in identifying the cause of the crash. The second metric that every single predicate is scored on is how early in the program the predicate is. As we talked earlier, differences in behavior near the beginning of the differences in behavior are more meaningful early in the program because they are more likely to be related to the root cause of the crash. So the earlier in the program the predicate is, the higher score we'll get. And so next we go on to the experimental results. So for this paper, Aurora was evaluated on 25 different bugs in various software packages. These are very common software packages such as PHP, Python, Bash, and Ruby, as well as Lua and Perl. And this was evaluated on many different things. For example, the number of predicates as well as the number of lines of source code that each single bug had to have looked at in order to identify the root cause of the crash. In order to find the root cause of the crash as well, these were from now patched versions of the binaries, so that the patches could be used as a reference to find out where the root cause actually was. So no guesswork was involved. These predicates were also based off of, AURORA was also based off of the top 50 predicates that were scored based off of how accurate they were at identifying between non-crashing and crashing inputs, as well as how close they were at the beginning of the program. They were sorted by if they were true positives or false positives. And we can see that typically AURORA was able to mostly have true positives and not as many false positives, but that wasn't always the case, such as for number 6, where the false positives outrank the true positives, in number 17, where you have 43 false positives, only 7 true positives. Number of predicates and lines of source code that had to be looked at were also relatively low, but could go up as high as 215 for predicates and 141 for source lines of code to be looked at. However, overall, the developer fix appeared quite early in the list of predicates that had to be looked at, which helped reduce the number of lines that had to be analyzed by someone who was triaging in order to fix a bug that a given crashing test case from a fuzzing campaign to analyze, which can help reduce the triage bottleneck that occurs in many fuzzing campaigns. So yeah, if you have any questions, please let me know. And I appreciate you listening to my talk.